My husband left the monitor on. Hold on, you're gonna hear lots of screaming in a second if I don't turn this off. Screaming is just their default. Okay, good, wonderful. All right, so we were talking about some questions some people had on the homework. I was really pleased to see everybody had logged on like really early on the WebAssign, like Monday night, and got going. So I'm glad that people got started on that quickly instead of waiting until like 2 p.m. today. So that was very positive. Were there any other questions on the homework that you guys wanted to go over? I kind of wanted to talk about those complex fractions on the review sheet, but I don't actually think I had assigned any of those on the algebra pre-calc review. I should look and see if I can see that. There might not have been any to assign.
I do have a question on a math question for the homework. I just have to find it really quick.
Okay. Go ahead. Where's my window? Let's see. Yeah, it was a lot of function stuff that was available. They might not have really had anything available for simplifying complex fractions. Gotcha.
Yeah, so could you explain how to do number 28?
Yes.
Because I had a bit of trouble with the arctan. I think that's what it is.
Oh, okay. Yes. Mine is the inverse tangent of the square root of 3. What's yours?
Mine's the same thing.
Same thing. Okay. So I put up for you guys, I don't know if you saw it in your D2L. So let me fix this. It was like a trig cheat sheet kind of a thing, and it had in there a whole unit circle. If I can find it.
It was really helpful. Thank you for that.
Well, good. Yeah, and you can use that on your tests. It's kind of nice because everything is just right there. Here's my suggestion for when you're not sure about what your trig values are. Because, I mean, of course, ideally, I would love for you to have them memorized. But honestly, if all you have memorized are the sine and cosine values, that's really all you need. If you just remember, I don't know, even just for these two, sine of pi over 6, I did not do a very good job with this makeshift chart I was just thinking about doing. Sine theta, cos theta. Okay, so sine of pi over 6 is a half, cosine pi over 3 is a half, cosine pi over 6 is root 3 over 2, sine pi over 3 is root 3 over 2. If you remember these 4 things, and then you remember all students take calc, what quadrants your angles are negative and positive in, that's really going to be most of what you need for these exact answer problems. For something like this, if you wanted to do it just by trial and error, you might be thinking like, okay, I know it's either pi over 6 or pi over 3, but I can't remember which one it is. As long as you use the identity that tangent theta is sine theta over cosine theta, then you can try it out and see which one ends up giving you the square root of 3. Because remember that the inverse trig function is an angle. That's what we're trying to find here. We're trying to find the angle such that the tangent of that angle is the square root of 3. So find theta such that tan theta equals square root of 3. That's really what that question is asking you, just in different words. So if you are wondering, like, okay, maybe I'll take sine of pi over 6 over cosine pi over 6. Like maybe you thought the angle was pi over 6 because you know it's probably one or the other. You can't remember. So you're going to try this one. Well, if you know the sine of pi over 6 is a half and the cosine of pi over 6 is the square root of 3 over 2. Then you'll get 1 over the square root of 3. When you rationalize that, well, first of all, you already know that 1 over the square root of 3 is not equal to the square root of 3. So right off the bat, that can't be it. And even if you tried to rationalize it, you would multiply by the square root of 3 in the numerator and the denominator, and you would get root 3 over 3. Well, right there tells you that the tangent of pi over 6 is root 3 over 3. So if you even wanted to add that to your table, the tangent of pi over 6 is root 3 over 3. Well, now you can go ahead and say, okay, it's obviously not pi over 6. Maybe it's pi over 3. So the tangent of pi over 3 is the sine of pi over 3 over the cosine of pi over 3, which is the square root of 3 over 2 divided by a half, which does indeed give you the square root of 3. So your answer here would be pi over 3. And you're being asked for the actual inverse tangent value for number 28. Sorry, I've lost it again. Yeah, so you're not looking for like 2 different places where you're getting this particular value. You're just being asked for the inverse tangent value. So there's only one of those, and that is pi over 3. So that's how you would do that. So that's my suggestion to you, really, is just know these 4, and then the rest of it, I mean, for the tangents at least, you won't have to worry about memorizing which one's which. You use this enough, though. I always think of the more complicated one as pi over 6. I don't know why. And then the easier one's pi over 3. I don't know why. That just is what sticks in my mind. All right, so that was number 28. Any more questions on that, or any other questions from the homework that you guys had? Don't be shy.
I had a question on number 14. Like, I think it was like f of g, g of f, f of f.
Let's see. 14. Oh, the composite functions. Yeah. Okay. Hold on. I'm going to verify that you can see this in a second, but I have f of x is 2x and g of x is 3x squared plus 1. You're being asked for, let's see, f of g of 3, g of f of 4, f of 1, and g of g of 0. Yikes. I won't remember what that one says in a minute. Okay. So for composite functions, we're not going to be spending very much time actually finding composites of functions, but we are going to be working on the chain rule, which really is a way of working with composite functions for calculus, and also undoing the chain rule when we talk about integration by substitution later on. So we will be working with actual composite functions, even though we won't be spending much time composing them. So for something like A, you're looking for f of g of x. Oh, and they just want this value at 3. So you're really looking for, right, they want f of g of 3. So f of g of 3. So you're looking for f of g of x at 3. You have 2 different options here. You can either find g of 3 and then find the f value there, or you can find f of g and then evaluate it at 3. The easiest thing to do here would just be to find g of 3 and then evaluate f at that value, because you're not being asked here at all for the actual like f of g of x. So you can go ahead and find g of 3 and then find the f value. So I know that g of 3 is going to be 3 times 3 squared plus 1, just because I'm looking at this g function. 3 squared is 9 times 3 is 27 plus 1 is 28. And then you're looking for f of 28. So f of x is 2x. So f of 28 is 2 times 28, which is 56. Some of these values might get kind of big. But you're going to do the same thing for all 4 parts here. The difference is that you're going to be composing different functions for different parts. So for g of f of 4, it matters that that g is your outside function. So you're first going to evaluate f of 4 and then evaluate g at that particular value. So f of 4 is your inside function. F of 4 is 2 times 4, which is 8. And then g of f of 4 is just g of 8. So g of 8 would be 3 times 8 squared plus 1, which is 3 times 64 plus 1. I don't know what 3 times 64 is. 192. Add 1 and you get 193. So you would do the same thing for C and D. The only difference is you would just be composing your functions slightly differently because you have f of f and g of g. But same idea for both of those. Anything else from the homework? It seemed like I got a lot of questions about trig. We're going to do a lot of trig in this class. I was telling my class last semester that one summer I was teaching calc, and I was like, okay, guys, we're going to be doing a lot of trig today. And one of my students said, it's time to get triggy with it, because there used to be a song called Getting Jiggy With It, Will Smith. So every time I say we're going to do trig in calc, it reminds me of that young man in my class. And now here we are like 10 years later, and everyone's like, what song are you talking about? It was old even then. But still, if I say we're going to get triggy with it, that's what I'm talking about. So it makes me happy. All right, anything else from the homework? Wonderful. From your algebra trig review sheet that I gave you last time, if you still had questions on that, feel free to ask me in the office hour and we can go over it. I did post the key, so you should be able to reference the key and then see if it makes sense to you. And if not, feel free to ask. I did, though, I feel like the log stuff is pretty straightforward. I do want to talk about simplifying complex fractions just because it's something we're going to be doing a lot of, and that's on the last page of this sheet. And then we'll talk about calculus. I took my kids to the splash pad today, and I'm always trying to get sun because I'm like super, super pale. And the thing about getting sun is you never know until several hours later if you were successful, and then you realize that your like whole body is burning. I don't necessarily know that that's going on, but I definitely feel a little bit uncomfortable right now. So maybe I'm starting to get some color. I don't know. We'll see. Okay, here's my review sheet. All right, simplify the complex fraction. So first of all, I want you to notice the difference between something like A and something like B and C. So B and C have more than one term in each part of the fraction. A just has one term. Now, terms are quantities we add and subtract. There's no adding or subtracting going on here between fractions. Now, in this problem, we have adding and subtracting. So I'm taking a fraction, I'm adding it to another fraction. In this problem, I'm not really thinking about what's happening inside the particular subfraction. I'm mostly worried about something like this, where I'm adding two fractions together within a part of the fraction. Now, depending on what's actually happening with your particular problem, your method for going about simplifying these might be slightly different. So it matters, for instance, to me that in part A, I don't have more than one term in any part of the fraction. So for something like A, when I go to simplify this, I'm thinking about this more like a division problem. I'm just dividing two fractions. And you know that if you divide two fractions, you just multiply by the reciprocal. That's going to be the easiest way to do this if you only have one term in each piece of your fraction. So I would just take the numerator of the fractional numerator of your complex fraction. And by the way, a complex fraction is a fraction that has a fraction within the numerator or denominator. And then you can rewrite this as division first if you'd like. Instead of showing this using that vertical division, you can just straight up show it as a division problem. I'm really taking 2x divided by 27y squared and dividing it by 6x squared over 9. And then switch this over to a multiplication problem. This is the way you were taught to do this a long time ago in algebra. And by the way, if this is bothering you because you're like 6 over 9, why are we dealing with this? It's not even simplified. I mean, you can go ahead and reduce. I would say that 3 goes into 6 twice, 3 goes into 9 3 times. We know that 6/9 is also known as 2/3. So if that's bothering you, you can go ahead and reduce now. But when I invert and multiply, the denominator is going to become my numerator, and the numerator is going to become my denominator. So now instead of 6x squared over 9, I have 9 over 6x squared, which we already reduced to 3 over 2x squared. So that'll make our work a little bit easier. But now you can go through and finish this one out. We can go ahead and take out a 2x, by the way, here, and a 2 and an x there. But I can't take away both x's right here. I can only take away one of them. So I still have one factor of x. Sometimes I circle it just so I don't forget that it's still there. And then we have 3 over 27. 3 goes into 3 once. 3 goes into 27 9 times. And then when we simplify, we'll get 1 divided by 9 times x times y squared. And that's how you would simplify that particular complex fraction. So that one's a little bit easier to work with. You won't really see as many of that type. Now, technically, if you have something like what we would see in B, you can also do it this way. The only difference is you would have to simplify each subfraction such that you had a case like this. So you would have just like a fraction, one fraction in the numerator, one fraction in the denominator. And some students do it that way all the time. They feel more comfortable doing that. So they simplify the numerator, simplify the denominator, invert and multiply. The method that I'm going to be using in class, and since I'm going to be doing it, you probably want to make sure you know this method because I don't want you to be confused, is multiplying every term by the LCD to simplify the complex fraction. So if the numerator or denominator of your complex fraction contains more than one term, multiply by the LCD. Multiply each term by the LCD of the denominators. This is another one of these topics that every once in a while gets skipped in an 098 class. I don't know if any of you took 098 at ECC. I once went to sub for a teacher in an 098 class, and he was supposed to be covering this. And the notes he left me were, if you don't have enough time to cover this, no big deal, we'll probably just skip it. And I was very upset by that because that particular teacher didn't teach calculus and didn't understand that we actually do this a lot in calc, and it's an important skill to know. So I did teach it to the class. But when you learn to do this, at least at ECC in the 098 class, you learn to do it using two methods. One of the methods is this one. The other method is multiplying each term by the LCD of the denominators. So you're going to look at the denominators, and your LCD is going to contain each factor the greatest number of times it appears in any one denominator. So looking at all four of your denominators, you have a y squared, an x, and an x squared. So I know I need to use the variable y. I need to use it the greatest number of times it appears in any one denominator. So I need a y, and I need 2 of them. And I need an x, and I need 2 of them. So my LCD is going to be x squared, y squared. What you don't want to do is say, well, I have a y squared and I have a y, so doesn't that mean I need a y cubed? Yes, you can technically create a common denominator, but it won't be your least common denominator. So it's not the end of the world. You're just going to have to simplify it further if you choose a common denominator that's not the least common denominator. Don't make more work for yourself than you have to. Does anyone have a question about where I came up with this LCD? So what I'm going to do now is I'm going to go through and I'm going to multiply each term of this expression by the LCD. So I'm going to multiply here and here and here and here. Now the whole purpose of this is that I need to get rid of any subdenominators. So by the time I'm done with this, I should only have a fraction that's not a complex fraction, that has nothing additional in the denominator. But each term, remember terms are things that we add and subtract, needs to get multiplied by that LCD. Sometimes students will show this with parentheses and they distribute it. I think it's easier to see if you just straight up multiply each term. Cancel out what you can in each term. So the y squared and the y squared, gone. The y and 1 factor of y, gone. And again, if you want to circle it so you know you don't forget that it still exists, that's fine. I'm always surprised at how often I lose variables. The x squareds are going to cancel in that lower left term. And then you can cancel out 1 factor of x and the lower right term. I'm going to circle the one I have left. Now, I've canceled anything out that I could, and now I just need to simplify. Questions here? All right, so when I multiply through, the y squareds are gone in this upper left term. I have an x squared times an x, which is x cubed. I have a plus sign between my terms. The y in the denominator is gone, but I have an x squared y in the numerator. In the denominator, the x squareds are gone in the first term. I just have a y squared. Oh, times a y, which is y cubed. Almost forgot about the existing y. And then I have a plus sign, and then I have an xy squared, or y squared x. It does not matter what order you write that in. We usually do it in alphabetical order, but that's up to you. Now, this one can actually be simplified further because notice that in the numerator and denominator, we have a GCF. So I can actually take out a common factor of x squared in the numerator, and that leaves me with x plus y. And in the denominator, I can take out a common factor of y squared, and that will leave me with y plus x. Now, y plus x and x plus y are the same thing. Now we have common factors. They're common factors because they're being multiplied. Once you have it factored out, you can cancel it. So technically, my simplified answer is x squared over y squared. What I don't want to see you do, and this is a very, very common mistake. I'm going to rewrite this so that you can, I don't want to butcher my example here, so I'm just going to rewrite it. Okay, this is one of the most common math errors of all time in any class, even calculus. Students do this all the time. I'll show you what not to do. Don't do this. They say like, okay, I see a common factor of y. I can take that out, and this leaves me with x cubed plus x squared divided by y cubed plus xy. Oh, and then look at this. I can, oh, you want to see something even worse? X to the 5th. I can't tell you what kinds of crazy stuff I've seen. If you're looking at this and you're like, oh my gosh, this is nuts, I would never do that. You never know. I've seen crazier things, and maybe if you were in a situation where you were under a lot of pressure, you might do silly things. Okay, the first major mistake that I made was factoring out before I canceled. You have to have common factors in order to cancel. Renee, what's your question?
So when you were adding back in your variables, Isn't it supposed to be 1 over x squared y and then 1 over xy squared?
Which part of the problem are you looking at?
So the first part, so we're it's still printed on before you wrote it. So yeah, it's like so you see the two fractions that you have, the 1 over y and the 1 over x. Where do those ones go?
Oh, the ones just get multiplied. So this was just like 1 times x squared times y. Is that your question, that we should have like added them?
Yeah, no, I was a bit confused. So I didn't know that you added them.
Oh, no, you don't add them. That's what we didn't do. So the ones, technically, okay, so like in the first term, you see that we had this x here. So we had x times x squared, and that's where we got our x cubed. And then for the second term, we do the same thing, except we don't have an x, we have a 1. So we're just taking 1 times x squared times y.
Okay.
Is that answering your question?
Yeah, that answered my question.
Okay, good. You're doing such a nice job with the hand raise. I don't know if I never had that feature, if that's a new feature to Google Meet, but I really like it because I think it takes away the awkwardness that students have when they're like, I have a question, and then they feel bad that they're interrupting. The hand raise is great because then, it gives me a second to kind of catch up to a spot where I feel like I can answer your question. So, so that's good. Okay, so down here, you cannot cancel between terms. You can only cancel between factors. And I did not actually factor out the y, so I can't cancel it. And notice that I couldn't have factored out the y because it wasn't common in every single term. I can only start to cancel if I have 1 in every single term. So if I had a y here, well, that's fine. I could have canceled the y everywhere, but I didn't have that. If you cannot cancel it out, then you cannot factor it out. I'm sorry, I said that backwards. If you cannot factor it out, then you cannot cancel it out. And we could not factor it out here. We can't cancel it out. The other big thing is that x cubed and x squared, when you add them, they don't give you x to the 5th. You cannot do that either. This is another very common mistake. You actually can't combine these at all. You can only combine terms that are like terms, which means that they have to have the same variables to the exact same exponents. This is, you cannot do that. No. If you had x cubed times x squared, then yes, you'd get x to the 5th. X cubed times x squared is x to the 5th, but not x cubed plus x squared. So, so this is all bad. This is a big don't do this. This is bad. Don't do that. And then, yeah, we'll do one more just because, like I said, we're going to be doing a lot of simplifying complex fractions in the upcoming chapters. Any questions on B? Any other questions? Wonderful. C. This one is one that you're going to want to factor before you mess around with it. Notice that x squared minus 4 is actually the difference of 2 squares. So when you factor this, you're going to want to rewrite it as x plus 2 times x minus 2. And I always have at least one student who's like, wait, huh? What? Difference of 2 squares is a squared minus b squared, and it factors to a plus b times a minus b. Okay, so that's going to help you to find your LCD. I do have a big fraction here in the numerator. Now, I would consider this to be just one fraction. So if in the denominator I just had one fraction, I would invert and multiply. But in the denominator, I'm adding 2 fractions together. So I'm going to go ahead and multiply each term by the LCD. In order to do that, I need to first determine what the LCD is. So I'm looking at my denominators. Here's one. It's got x plus 2 and x minus 2 as factors. Now, in this denominator right here, I have an x minus 2. Each one of these denominators has an x minus 2. I need to just use it as many times as it appears in any one denominator. So I'm just going to use it once because I only see it once here in the denominator and once here in the numerator. 1 is just 1 over 1, so your denominator there is 1. So my LCD is just going to be the two factors that I actually see, x plus 2 and x minus 2. Any questions on the LCD? Now, remember that even though you see x minus 2 twice, you only see it once in any single denominator. So we're only going to use it once. And again, if you had used it twice, you would still get a common denominator, just not the least common denominator. So I'm going to go ahead and multiply through in each term by the LCD. I'm going to multiply it in the numerator once because I only have one big fraction in the numerator. And the denominator, I have two fractions, two terms in this case. And I'm going to multiply each term by that LCD. Now, the LCD is actually the denominator of the numerator, so both of these factors are going to cancel. In the denominator, all right, here in the first term for 1, I can't cancel anything. But in the second term, I'm going to cancel out the x minus 2's. But remember, the goal here is just to make sure I get rid of all of these subdenominators, and I have successfully done that. So now we can rewrite the problem. In the numerator, I just have x minus 1 because I canceled out the whole denominator. Both of those are gone. Now in the denominator, I'm taking 1 times x plus 2 times x minus 2. So I have x plus 2 times x minus 2 plus, and then 1 times x plus 2 is x plus 2. The parentheses are non-essential. That's up to you if you want to use them. And then you're going to just have to simplify. Before I do that, are there any questions on the simplification or the undoing of the complexity of the fraction? Right. Numerator is x minus 1. The denominator, we already said that x plus 2 times x minus 2 is x squared minus 4. But if you forgot that, just refoil it, and you'll see that. Remember, we already kind of did that work. And then simplify. So you have x minus 1 divided by x squared plus x minus 2. Now, this one's a little bit trickier because you can actually factor the denominator and cancel out a common factor. The denominator is going to factor the two numbers that multiply to -2 and add to 1 are -1, +2. So you'll factor that, and then once it's factored, you can cancel out a common factor. Now, remember that when you cancel out the common factor, if that's all you have in the numerator, you still have 1 at the end of the day. X over 1 divided by, x minus 1 divided by x minus 1 is still 1 over 1. Sometimes students say, oh, I took away the whole numerator, now it's 0. It's not 0. X over 1, x minus 1 over x minus 1 is 1 over 1. So we still have that 1 in the numerator. All right, that's all I wanted to say about the algebra trig review. If you have other questions on that that you felt weren't very, you still weren't sure about after looking at the key, please let me know. It is up on D2L. Just somewhere here. Okay. So today I want to talk about limits of functions using numerical and graphical techniques. This is pretty much always the first thing that you start learning about in calculus after a brief review. I never used to review in calculus, and then it was suggested to me one year that I should, just because so many of my students seem to lack those prerequisite skills. And I was complaining to my dean about it. She was like, that's fine, spend some time reviewing. Some teachers do, some don't. I do think it's a good refresher though, rather than all of a sudden realizing you need the skill and you're trying to kind of scramble to remember what it is. Goes here. One point one. Limits of functions using numerical and graphical techniques. It's like so quiet in this room and all I hear is like my 4-year-old down there just yelling. It's like he doesn't know how to just speak. He only yells. He's like unbelievably loud. Okay. So let's talk about limits. I'm going to give you sort of an informal definition of a limit. If you've taken calculus before, either in high school or maybe you took it with a different instructor at ECC before, you might have been asked to work on something called an epsilon delta proof. I'm not going to make you do that. I used to make students do that, and I felt like they didn't really get a lot out of it, and it was just a struggle for no purpose. But I do want to make sure that we actually talk about what a limit is, because it's important to your knowledge of calculus. So I will give you a definition of a limit, and then we'll talk about how to find limits. I remember when I was a student at ECC, I was in Trig, and one of my friends was in Calc 1, and he was so confused, and he was just like, oh my gosh, these limits are killing me. I don't know what's going on. It's so confusing. And then I took Calc 1 thinking like, oh my gosh, like I'm gonna have to learn these limits and it's gonna be terrible. And it wasn't terrible. It's not supposed to be terrible. I'm gonna try to explain this to you in a way that is very approachable so that you don't think that limits are this terrible, scary thing, because they're really very intuitive, I think, as long as you have some sort of understanding of the concept of approaching a number, which I think most students have. So what we're going to be looking at here notation-wise is the limit. I'm going to write this out in English words too, so you know what this means, of f of x as x approaches c is some value L. So this is, in English, the limit of f of x as x approaches c is equal to L. So it's really important that we understand how to actually say our notation in English words. Otherwise, you'll be in the office hour and you'll be going lim f of x, x arrow c. It's going to be very hard for you to communicate to me what's going on. The limit of your function f of x as x approaches c is L. It's really important that the function is actually on your limit. You can't just take the limit of nothing. I can't tell you how often students tell me that lim x approaches c equals, I don't know, like 5. That's not proper notation. You can't just take the limit of nothing. And it's not like it's an implied 1. And even if it was, we would have a rule for that. You have to have some sort of function that you're working on for this limit. So you can't just write lim equals. It doesn't work that way. Okay, so that's the first thing, notation. Someone is raising their hand. Oh, it's Burfin. Okay, Burfin, what's your question?
I can't read what you said. The limit of f of x, and what does it say there?
As x approaches c.
Oh, it's as. Okay, thank you.
Yes, you're welcome. Okay. All right, anyone else? Questions before we dive into this? Okay. All right, so I'm going to give you sort of a rough graph here. Yours does not have to exactly look like mine, but it should have that same general idea. All right, so what we're going to do is look at some value of C, and we're going to put C in a neighborhood, and this neighborhood is going to be maybe bound on the sides by A and B. And I'm in this neighborhood. I'm going to put these open parentheses on here because I want to show that we can approach A and B, but we don't necessarily have to be equal to those values. And then we're going to look at what happens as our graph kind of runs through a point at C. So let's say that maybe I have a graph that kind of does something like this. Now, the y value at C is going to correspond to your point just by kind of moving it over horizontally so you can see what's actually happening on the y-axis. So what you're seeing here is that we have this neighborhood of x values that's on both sides of your point C. So we have this space between A and C, and then we have this space between B and C. And we have some values here that we're going to just kind of move around here that will correspond to certain values of your function on the x-axis and the y-axis. We're going to let y be equal to f of x. But in our neighborhood, what we're going to be looking at is what happens as we approach C from both sides. So no matter what, as long as I'm sitting somewhere in this neighborhood of my function, if I'm approaching this x value of C, if you can kind of imagine moving this neighborhood closer, I don't know, we can call it like B sub 1, you'll start to see that we can narrow into just a range of values for which we would have a y value for C. So if I'm looking at kind of getting closer and closer and closer to C, well, what's going to happen here is my y values are actually going to get closer and closer and closer to the function value for C. You can even make this a little bit smaller and call it B sub 2, smash it in there. And what happens then is, again, we're getting closer and closer and closer to C, and our y value is getting closer and closer and closer to the function value at C. This is all that a limit is saying, is that as I approach the x value C, my y values are also approaching some value of L. And the value of L that they're approaching is your limit. And in a lot of cases, your limit is going to be the actual function value at C, just whatever your y value is. That's not always going to be the case. Sometimes your function may not be defined at C. You might have a hole in your graph there. We'll look at a case where that could happen. I mean, imagine if you had a similar graph. It doesn't have to be exactly the same. We can make it look kind of the same. But maybe you have a hole at C. I made that hole a little bit too big, but that's okay. But you can see here that as you sort of move through this neighborhood and look at values of the function as you get closer and closer and closer to C, your function value is going to get closer and closer and closer to the function value at C. Now, you don't actually have the value at C existing in this case because there's a hole in the graph and the function doesn't actually exist there. But you still are going to have a limiting value. You're still going to have a value that your function approaches as you approach the x value C, no matter what. So even though you can't actually attain this value, you're still going to approach whatever this y value is. So the function value wouldn't exist, but the limit would. And that's what we're really going to be doing today, is talking about either looking at this graphically, like what I've done in these two like sort of sub examples, or looking at these numerically. And later on, tomorrow, we're going to be talking about how to do this analytically. So that means using algebra. So you're going to have a bunch of different techniques for finding limits. If you feel that you found the limit and maybe you've done it through one approach, but you're not sure, you can always check it using another method. So I'm going to make sure to specify on your exam if I want you to do it a particular way. And I will specify, find this limit using a table, find this limit graphically, find this limit using algebraic methods. But you will know what I expect you to do, but you should be able to sort of work through these methods for each example. The first method that I want to talk about is using a table. And we're going to be using our graphing calculators pretty heavily here, so make sure you have those handy. But I'm going to give you an example of how to find a limit numerically. We're going to go over a couple of these, and I think you'll start to get a pretty good comfort level with them. And then later on, we're going to revisit these same functions again when we talk about how to find limits analytically. And most of the time, you'll find that it's easiest to do them algebraically or analytically versus using a table, which is a little bit more cumbersome, but it works. Tables are great ways of doing this. So example 1, we're going to investigate the limit using a table. And then we're going to look at the graph in your calculator, and we'll also look at the tabular values in your calculator as well. Investigate the limit using a table. Is anyone else having a hard time? Because somebody emailed me and said they were having a hard time seeing my what I'm writing on my paper. I've never had anybody say that before, so I didn't know if that was a problem this semester. And since Burfin had asked me, I just wanted to make sure that wasn't an issue. Is anyone having trouble seeing what I'm writing?
Nope, it's all good.
Okay. All right. All right, thank you. Wonderful. I've been using the same software since COVID hit. I somehow got really lucky and got myself this document camera, and it was like the last one in the world, apparently. But I don't know what I would do without it. What would I do? How would I teach math? So I got very lucky. Some teachers were using like whiteboards and writing on them behind them, and I'm just like, how do your students see that? I got very lucky. Kind of in love with my document camera. Just saying. So first we're going to look at the limit as x approaches 2 of x cubed minus 8 over x minus 2. Now, in this case, our value of c is 2. So we're trying to figure out what happens at 2. Now, notice, by the way, that there's a reason I'm looking at this function at 2. It's not that interesting to look at this limit anywhere else. Notice that the value that's excluded from the domain is 2, because if I let x be 2, then I'm dividing by 0. And actually, I have an even bigger problem because 2 cubed is 8. 8 minus 8 is also 0. So if I was thinking about the actual function values here, and we're going to be doing that in the next section, I'd have a major problem here with this limit. But I can do this using a table, and then I can get a really good sense for what value of y my function's approaching as I approach x on both sides of 2. So I'm going to go ahead and set up a table. We're going to have to look at what happens as we approach 2 and get closer and closer to 2 on both sides of in that neighborhood, and the neighborhood on the left and the neighborhood on the right. Now, it is up to you exactly what values you choose. But if I were you, I would not approach 2 by using 0 and 1 and 1.5 and 1 3/4. That's not close enough. When we're talking about a limit and we're talking about zeroing in on a value and trying to narrow down what's happening, what we're trying to do is get really, really, really close to the number without actually touching it. So what I'm going to look at here are values that on the left of 2 get super close but don't actually attain 2. So I'm going to make a table here for my x and y values, or I should say x and f of x, I guess. And I'm going to put my value 2 in the middle. And if you're kind of correlating this to what we did in your graph, c is going to be that middle value, and then we're kind of narrowing in on what's on both sides of it. It's sometimes a little bit easier to do the values on the right. So you might need to fill in some more spaces, but for this one, I would say the closest you need to get on the right of 2 is maybe like 2.001. So you're just moving a little bit further away, but nothing too crazy. And then you can drop off a decimal place. And you can drop off another decimal place if you want. Maybe do something like that. But this is what's happening as you're leaving 2. So 2.001 is closer to 2 than is 2.01. 2.01 is closer to 2 than is 2.1. So you're sort of moving further away from 2 as you move to the right. Sometimes I would say go to 2.25, but that's not going to be very interesting. These numbers should be good. If you feel like you don't have a definitive view of what's happening, you can always plug in some more values. Now, as I approach 2 from the left, I might get as close as like 1.999 and maybe like 1.99 and maybe 1.9. Something like that. So you're at 1.9, then you're getting closer by getting to 1.99, closer still by getting to 1.999. So these are pretty standard values that I would use as I make a table to investigate my limit. Now, I'm going to show you how to do this in your calculator. This is all going to be calculator work. I don't want you to actually be sitting here by hand trying to find these weird function values. First things first, go to your y equals. Make sure that you're in function mode. I don't know why any of you wouldn't be in function mode unless you borrowed your calculator from someone who just took Calc 2 or Calc 3. You might be in parametric mode or polar mode. But you should have a bunch of y equals here. I'm going to plug in my function. When I do that, I'm going to be really careful with my parentheses, because if I don't use parentheses, then my function is going to look like x cubed minus 8 divided by x minus 2. And I don't want it to look like that. I want to make sure that it looks like x cubed minus 8 divided by the quantity x minus 2. So x cubed minus 8, close off your parenthesis, divided by, open up your parenthesis, the quantity x minus 2. Those parentheses are essential. Yes, who's raising them? Oh, Morgan, yes. What's your question, Morgan?
This is probably a stupid question, but how do you put an X on your calculator?
Oh, not a stupid question. It's the variable button here. So the x, t, theta, n. It'll give you an x as long as you're in function mode. If you take Calc 2 and you do parametric mode, it'll give you a t. If you do polar mode, it'll give you a theta.
If I use alpha x, it will be the same thing, right?
If you use alpha x, I don't think it works the same way. It'll give you an x, but I don't think it gives you the variable x. It could give you, and I guess it depends, because you might have something stored as your value of x. I don't think it works the same way. I'm really glad you asked. We could try it and see. You want to try it and see? Because it is a common thing to want to try to do. I'm surprised that they even give you an option for that. I don't know if you use alpha x. You can try it and see. Something tells me it doesn't work, but I don't know. Maybe I'll try it real quick and see alpha x. Oh, it does work, I guess, but I think it's faster to use your variable button, but it's up to you. If you have something stored in your x, it won't work, and then you'll not be sure why nothing's happening. That's the only thing I would caution you to. Any other questions about entering this into your graphing calculator? Okay, so what I want to do is I want to go to my table, but most of you probably have a table that's set up to give you automatic values. So what you want to do is go to your table setup, because if you're looking at automatic values, most of you are going to see 1, 2, 3, 4, 5. Well, I don't want to know x equals 1, 2, 3, 4, 5. I want x to be 1.9, 1.99, 1.999. And if I want that, I'm going to have to make that happen. So I'm going to go to second window, which is my table set. Now mine is set to ask for my independent variable. Make sure yours is set to ask. Yours is probably set on auto. It might not be, but if it is set to auto, move it over to ask and hit enter. This stuff is not going to matter if you're on ask. Whatever you do, don't change your dependent variable. Make sure your dependent variable is on auto. It's only your independent variable that you want on ask, because you're going to be asking about your independent variable x. F of x is dependent on the value that you enter. Oh, sorry, I'm missing something in the chat again. Oh, someone is saying that they cannot see what I'm writing. Is that the case? I'm not sure how to pronounce your name. Is it Nawal? I'm just looking at the chat, and someone said that they could see what I was writing, and someone else said that it was not good for them. Okay, well, you can let me know what the issue is. I don't know if it's like blurry. Oh, by the way, the person who had emailed me, I suggested that they check out a Chromebook from the ECC library. So you always have the option of doing that, and that should work better for you than using your phone if for some reason your PC doesn't like Google Meet. I know those, like Zoom takes up so much of my computer's energy. And I always hear it like going crazy. I don't know if Google Meet does the same thing, but Chromebooks work really nicely with anything Google or Google. Okay, so you should be set to ask. And then when you go to your table, mine has a bunch of values in it because I have entered a bunch of values in it, but yours should have nothing, which is perfect. I forgot how to clear these, but that's fine. I don't need to clear them. Yours is going to be empty. What I'm going to do is I'm going to start entering values for x in here. And since I'm going to be looking at all 6 of these values, I'm just going to go ahead and start entering them. Oh, her microphone isn't working. Okay. Well, that's okay. Why don't you tell me what it is that's, oh, you can see. Okay. Well, then what was the not me thing for? Was that not about my, sorry, this is, such is life with the e-learning. Sorry, I don't remember what the question I was asking for that you answered not me for.
I couldn't get on the table.
You couldn't get any table?
I couldn't get on it. Like, where do I press to see that?
Oh, I'm sorry, the table was a second graph.
Oh, okay, thank you.
Yeah, sorry about that. I went and did that automatically.
Got it.
Awesome. Okay, so I'm going to go ahead and enter these values in my calculator. I want 1.9. Just start typing. Notice how I entered 1.9 and I got 11.41. So I'm going to do that for all 6 of these values, 1.99 and 1.999. Now, it might be kind of hard to see my calculator. I don't know what to tell you on that. I can maybe try to zoom in on it, but it may not look that great. Let's see. As much as I wanted that emulator and I had a free trial and it expired, it was actually, it was very hard to go back and forth between the two. So I actually kind of like it better this way. Since it's summer, the light's better anyway. Okay, so these are the 3 values I have to the left of 2. The ones that I have, oh, notice that at 2, I get an error. I didn't actually enter that. It's just coincidental. 2.001, 2.01, and 2.1 are the values to the right. So we're going to enter these values into the table that we put on our notes. Does anyone have a question about how I obtain these values before I go back to the notes? Okay. So, Nawal, I don't know if I'm saying your name right, and your microphone's not working, so you can't even correct me. Send me an email and let me know what you're not seeing well. Because I've never had anyone say that before, but I don't know. I don't want there to be an issue. I want everyone to be able to see what I'm doing. Okay, so I'm going to go ahead and unzoom this. Oh, Victoria, yes, tell me.
I was just replying back to like what Noel said. They were just replying back to when you were asking if anyone had trouble seeing anything, and they were referring to like, oh yeah, like it's fine for me. I think that's what they were trying to do.
Gotcha.
So,
yeah,
yeah.
but then she was saying that, oh, that she can see.
Mm-hmm. Yeah.
Okay. Oh, she was saying, no, not me. I'm not having trouble seeing.
Yes. That's what they were trying to say.
She's saying, not me. I can't see it. And I was just like, oh gosh, well, that's no good. Okay. All right. Someone in the chat is asking, how do you put in the X values? Oh, you guys, e-learning, man. It's a lot. It's a lot of crazy. Sorry. It's not usually this crazy in my class. How do you put in the X values? So you should just be able to, are you in ask, David? You did set it to ask, right? Because if you don't set it to ask and it's set to auto, then you can't actually enter any X values. So once you have your independent variable set to ask and you go to second graph, you get your table. So second graph, your table pops up, and then you just start typing. So, I mean, cursor over where you want it to go. So I wanted my first, I think it just automatically defaulted to being blacked out in my upper left, but wherever you're hovering over, just that's where your value is going to go. And then you can just sort of kind of go along the line like that. Okay, good. Yeah, and my chat is not beeping at me. I don't know if it beeps at you guys. The hand raise beeps at me, but the chat is not beeping at me. So I have to like look over and notice that there's a blue dot on it, and I don't think to look over there very often. So it used to beep for me all the time. I don't know what's going on. Okay. Oh wait, I see a blue dot. Do we have to set it to ask every time? It'll stay like that until you change it back. So you have to manually set it to go back to auto if you want it to be auto. So the difference is if you set it to auto, oh gosh, I'm going to lose my values. I'll show you in a minute. I'm going to write down these values first before I lose them. Okay. So I have 1.41, or I'm sorry, 11.41. 11.94 and 11.994. At 2.001, we have 12.006, and then we're at 12.06 and 12.61. If you don't have a lot of familiarity with your graphing calculator, if you are on table set and it's on auto, it's going to start your table at 0, and your delta table is set to however many integers you want it to change by. So if it's set to 1, that means it's going to start at 0, and it's going to go 1, 2, 3, 4, 5, 6. And it's going to give you a table that looks like this. So not that helpful in our case because it's never going to give you these decimal values. You could always switch your tables, your delta table to like a half. And if you did that, I mean, you could even start it at 2 if you wanted to. And then you could generate your table, and it would give you every half value starting at 2. So that's how the table works. I mean, technically, if you really wanted to set your table up to be like 0.999, I don't know why that would be useful, but I'm sure there must be some time that it would be. You could just make it change by these really small incremental values of 0.999 each time. So you could do that too. But I want mine set to ask. So that's what I'm going to do. Okay. And then when I redo it, it goes blank. So I would have to enter the values again. So that's how your calculator table works. Okay, so the idea of the limit, the concept of the limit is that what I'm looking for is I know that I don't have a defined value at x equals 2. I've got a problem there. The function doesn't exist at 2 because I'm dividing by 0. But I can actually look in this case at what values my function is approaching. I can still find a limit for x approaching 2. And what that means is I'm looking for the y value that our function approaches as the x value approaches 2. So we're going to say the limit is kind of asking what value does y approach as x approaches 2. That's what you're really asking yourself when you're looking for this limit. And of course, y is synonymous with f of x, in our case anyway. So you're looking at these values, and if you're imagining that this is occurring on your graph, you're looking at 1.9, okay, you're getting close to 2, 1.99, you're getting closer. 1.999, you're getting even closer. And you can see now that the function values are approaching 12. And what you're going to do then is you're going to verify that the same behavior is occurring on the right-hand side. So as we were moving away from 2, we had 12.61. But as we get closer on the right, we're narrowing in on this value of 12. So we can conclude here that the limit of our function as x approaches 2 is 12. So you're going to make this logical conclusion here just by looking at your data and saying, okay, well, if x is approaching 2, what value does f of x approach? And that's how we do this using a table. We'll do one more, and then we'll talk a little bit about one-sided limits. Before I do one more, does anyone have a question on A?
So the answer is 12.
The answer is 12. Yeah, if you want to.
Do we put it? So that's the answer of like the whole fraction.
That's the answer for the limit of our
The
function.
limit, but we don't do anything in the function, do we? We don't. Okay.
You're just going to write 12. And WebAssign will have a, limit. And I think it'll just say the limit equals, and then you'll put the number in. Or it might say the limit is, and you'll put the number in.
Okay.
But your limit is the number that your function value is approaching.
Okay, thank you.
Anyone else? Questions on A? Because I know this is totally new to most of you. I didn't even look. My roster used to tell me if people were repeating the class, if they've had it before, not high school students, but if they had it before at ACC. But it doesn't say that anymore. Everything changes. Gotta roll with the changes. Let's do a trig problem so we can get tricky with it. I'm gonna do the limit as x approaches 0 of sine x over 1 plus the tangent of x. Now, this one might be a little more tricky. We're going to have to see. Okay. But no matter what, I'm approaching 0. So I'm going to be looking at values of x that approach 0. So it's up to you where you want to start. I'm going to use similar values that I used here. I might find that those aren't close enough, and I might need to get a little bit closer. Let's just get a little bit closer to start. It wouldn't hurt anything. So I'm going to look at x and f of x. So maybe instead of starting like 0.1 away, maybe we should start, well, we could start at 0.1 and then add in a little bit more. So we're approaching 0, and I find that sometimes students have a harder time with this when they're approaching 0. So if you want, move to the right first. Maybe go with 0.0001, maybe include 4 decimal places, and we'll see if we need more. 001, 01. I don't think you're going to need to get much further away, but who knows? Now, since we're talking about 0, as you move left of 0, you're going to be using these same values, but they're negative versions. So negative 0.0001. So we're going to get super close, but on the negative side of 0. Something like that. Oh man, I feel bad because the whole chat situation, you know, people are just trying to help me and be clear, and it turned into a whole fiasco. Now people are not going to want to say anything anymore. They're just like, oh, forget it. It's just confusing. All right, questions about the setup of our table? Wonderful. So go to your graphing calculator. Go back to your y equals menu. Delete the function you have by hitting your clear. And then you're going to enter the sine of x. Make sure you're in radian mode. You should always be in radian mode in this class. You will never need to be in degree mode, ever, ever, ever. But if someone borrows your calculator, maybe you have a younger sibling who's in high school, they use degree mode more often, make sure you check. I haven't seen students have that problem very often lately. So sine of x, close your parenthesis. You certainly don't want to be taking the sine of some major large function. Divided by. In the denominator, I'm dividing by more than one term. So I need to make sure I include parentheses around the whole thing. And so I have a parenthesis after the x to close off the tangent of x, and then I have another parenthesis to close off the denominator. If you forget that one, it's not a big deal. Your calculator knows what you mean. But if you forget this one, it is a big deal. If you forget that one, it is a huge deal. So make sure that your parentheses are in there. Okay, I'm going to go back to my table now. You should already be set up to ask. I'm going to go negative 0.1, negative 0.01, negative 0.001, negative 0.0001. And I'm going to know if I need to get closer because I'm looking at these values and I want to make sure I can see if I'm approaching a value. Now, notice that these numbers are actually getting smaller and smaller and smaller. Now, if you're getting, for the last one, e to the -4, I think there's a way that you can set your calculator so that you don't get that. But it just means times 10 to the power. So if you learned scientific notation, which all of you should have at some point, -1 times 10 to the -4th power is just one more 0 than you would have seen in your decimal point for the previous answer. So you can see how this number is getting increasingly closer to 0. It's getting larger, but it's zeroing in on 0. You can do the same thing now as you approach from the right. So if I actually entered 0, sometimes I do that just because, interesting that you actually get that value 0, which makes sense in this case because you don't actually have a situation where you can't evaluate the function at 0. Sine of 0, 0, tangent of 0, 0. So you're taking 0 divided by 1. Does that make sense? So that's another way. If the function value actually exists, then the limit will be pretty easy because the limit's just going to be the function value for something like this. But 0.0001, 0.001, 0.01, 0.1. And these are all the values you should be getting in your calculator. So I'm going to go ahead and enter those in our table. At -0.1, we have -0.111. And by the way, if I ask you to find a limit using a table on your test, which I will, this is what I expect to see. You've got a line for x, you've got a line for a row for x, a row for f of x, and you're just kind of zeroing in on that value, filling in your table, and then making a logical conclusion about the value of the limit. So let's see, you have -0.01, -0.001, and -0.0001. You can use the scientific notation if you want to. It's not a big deal. I just think it's easier to see the values if you just actually write them out. 0.01 is 0.0099. And then we'll have 0.0001. 8 times 10 to the negative 3 is 1. And then 0.0001. That. Okay. But you can see that your values are getting closer and closer to 0 in both directions. And the fact, like I said, that your function is actually equal to 0 when x equals 0 is another huge indicator. That won't always be the case if you have like a piecewise function or something else is going on. Kind of depends on how your function's defined. But if all I give you is this function by itself, and you actually have the function existing at the value at which I'm asking you to find the limit, then that'll be the limit value. Okay, so the limit is 0. That is your answer. Any questions on using a table? So I want to talk a little bit about one-sided limits and then just kind of show you some graphical representations of one-sided limits. And then I want to get into piecewise functions a little bit because I know you guys love them so much. Everybody does. All right, so that was using a table. This here. So let's talk about one-sided limits. We've sort of already been talking about this concept because we've set up our tables and we've kind of talked about what's happening to the behavior of the function as we approach from the right side and from the left side. We're going to formalize that a little bit more by talking about left and right hand limits. All right, so the left-hand limit, and we're going to have slightly different notation for each of these, very, very slight. This is the limit as x approaches c from the left. It's like a little negative sign, and it looks like it's kind of in the exponent of c. So the limit of f of x as x approaches c from the left is equal to the left-hand limit. So we just say L, and then there's like a subscript of left. This you're not going to really use a lot. You're going to have a number here that you're putting in here for your one-sided limit. This is just sort of the definition. So this is as x approaches c from the left. And of course, we're going to have something very similar for the right-sided limit. Although I have a note here about a box, and I'm looking at it now. The right-hand limit. Same idea. We're going to take the limit as x approaches c from the right. Instead of having like a little negative sign in the exponent, it's a plus sign. Of f of x equals the limit on the right. And this is going to be as x approaches c from the right. Okay, so I'm going to give you some graphs that we're going to be focusing on, for example, 2. We're going to talk about left and right limits. You don't have to copy the graphs exactly the same way that I've done it, but I'm going to try to just put some points on there so that it will be easy for you to sort of jot them down, because you do want them to be clear. We're going to use the graph to investigate the limits as x approaches 3. And the first one we're going to look at, we're going to plot a point, an open circle, at 3, 4. And then we're just going to have this be the vertex of our parabola. So it does not really matter exactly where it falls, what the x-intercepts are or what the y-intercept is, because we're really just going to be looking at what's happening as x approaches 3 on both sides. So we're going to talk about the one-sided limits, and then we're going to talk about the actual limit of the function. And I want to give you 4 examples here because I want to show you different things that could happen to a graph. And I think by being able to compare and contrast these examples, you're going to get a really clear idea of what a limit actually is, and feel like you can differentiate between when the limit exists and when it doesn't exist. So first, we're going to look at the limit as x approaches 3 from the left. Now, I didn't actually give you a function, so you can just say f of x. So what you're going to do here is you're going to follow the graph and approach your value of 3 from the left. Now, you're sort of thinking about 2 different things here, because you're trying to approach x equals 3, but when you do that, you're looking at what's actually happening to the y values on your graph. So I'm approaching 3 from the left. That means I'm actually heading right. Sometimes it takes students a little bit of time to get used to that, because when they think left, they think heading left, but you're actually heading to the right. You're approaching 3 from the left. So when you're approaching from the left, you're looking at values of x that get closer and closer and closer to 3. Well, as your value of x gets closer to 3, your value of y is following, it's going upward and following this upward trajectory of your graph. Up until you get to this value that you would approach at 4. Now, you don't actually have the circle filled in at 4, but it doesn't matter. You're approaching y equals 4. It does not matter that there's an open circle here and that you're never actually going to attain the value. A limit is all about the value that you approach. And I think sometimes that's the problem that students have with this. They keep thinking like, well, the value doesn't actually exist, so the limit doesn't exist, but that's not true. Limits are all just about what value am I approaching. So as x approaches 3 from the left, y is actually approaching 4. So the left-sided limit is 4. Now we're going to do this again for the right-sided limit, and then we're going to do it again just for the general limit of the function. If you feel like you might have a question, but you're not sure, and you want to see the rest of this done, then you might want to wait a minute and see. But does anyone have a question here?
Can you repeat it, please? Like with the 4?
Yeah, so it's sort of like when you're looking at, as you approach 3 from the left, your x is approaching 3, but your y value is approaching 4 because you're following the behavior of this graph. So as x moves further towards 3 from the left and heads right, your y values are following the graph. So your y values are going up, 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 and they're eventually going to, they would have hit 4 if you could have, but they're not actually going to get there. So the value of your function is just whatever value this graph takes on. So as you approach 3 from the left and head to the right, the y value approaches 4. Is that clearer?
Yes, thank you.
Okay. Any other questions? I know this does take a little bit of time to get used to.
I had a question.
Yes, go ahead.
Why was it 4? Was that just the number that you picked, or was there a reason for that?
Oh, this was just the graph that I drew. I mean, it's
Oh, okay.
4 because that's where I put this open circle at 3,
Okay.
4. That's why
So
it's 4.
when we get a graph, it'll have a point plotted like this?
Yes.
Okay.
Yeah. If you're being asked to find a limit graphically, yeah, they have to give you some sort of indication of where that point lies.
Okay, thank you.
Yes. Okay. Any other questions there?
Yeah, so if we approach the limit from the right, it's also going to equal 4?
Yes. And we will do that next. But yeah, absolutely. For the same reason. So if you're looking for the limit as x approaches 3 from the right, you're seeing the same behavior occurring because you have the symmetry here for this graph. But you'll approach 3 from the right. As your x values get smaller, you're following the behavior of this graph. X is getting closer and closer to 3. Y is getting closer and closer to 4. So yeah, for the same reason. Yes, Renee.
All right, and why are you using the y values as your answer instead of the x values?
Oh, the limit is always dictated by the y value because the y value is your function value.
Okay, okay.
So yeah, x will always approach a number, and when you're trying to find a limit, you're trying to figure out what value y is approaching. So your answer is always going to depend on the y value. Victoria, go ahead.
So I had a question on if there were to be like multiple plots. I'm assuming that we're gonna go over it anyways, but if there were more like multiple points, so let's say that there was one at like would there be one point that would refer to the limit being a different thing? So I don't know like how to like describe it, but like let's say we have a point at like 4, 3. Would that be like, would the y value be your limit to be 3 if it was approaching from like the right?
Yeah, and
If
you
that
probably
makes
would have
sense.
a point at 4, 3 for a function like this too, if it's a straight up quadratic.
Yeah.
I mean, I will, you're right. I am going to give you a bunch of examples here. So I feel like I will be answering your question in another couple minutes. But yeah, I could technically ask you to find me the limit if you wanted to plot a point there at 4, 3, and I could say, okay, what's the limit as x approaches 4 from the left? And you would tell me that the limit was 3.
Mm-hmm.
If that was the case. Or I could ask you, what is the limit as x approaches 4 from the right? And then again, you would tell me the limit was 3.
Okay.
Yeah.
Okay, thank you.
Mm-hmm. The last thing that I wanted to say about this graph is we don't only have to talk about one-sided limits. A lot of times we just look at the limit, like we did in the last example with the table. I didn't ask you about a one-sided limit, even though you technically did find them. We're going to talk about this general limit of the function. And in order for that to occur, we're just going to verify that really as x approaches 3 on both sides, what is the value of y approaching? And that's what we did in the last example. So you can see that in both cases, no matter which way we approach 3, whether it was from the left or from the right, the y value is approaching 4. So we can go ahead and make the conclusion that the limit of the function as x approaches 3 in general is 4. Like the function value is approaching 4 regardless of whether we approach from the left or from the right. So even though the function value does not exist at x equals 3, doesn't matter, the limit is still 4 because the function is still approaching that value. We're never actually talking about what happens at the point. We're only talking about what happens as we get infinitesimally close to that point. Really, 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 really close. Really, really little. tiny bit of distance away from that point. Get as close as we can. I'm going to show you another example, and then we can compare and contrast if you would like. So this one, I'm going to define, but I'm going to define it elsewhere. So we're going to still make an open circle at 3, 4. The graph is going to look a little different though, so don't make a parabola. And you can send a curve through there. Maybe something that looks kind of like that. As long as it has this behavior. And then 5, 6, 7, we're going to plot a point at 3, 7. Now remember, this is a function. It has to pass the vertical line test. I've removed the definition of the function from 3, 4 and moved it up to 3, 7. It's still a function. Technically, it's piecewise. I just haven't defined it like that because we're only talking about finding a limit graphically. All right, so we're going to talk about the limit as x approaches 3 from the left, from the right, and our general limit as x approaches 3. We're going to look at those things. All right, so we have a little bit of different behavior to follow in this particular example because we don't have a parabola anymore, but it does not matter. We're still going to be doing the same type of thing here. As we approach 3 from the left, again, you're looking at the values, you're looking at the value that the y values approach. So as x moves in towards 3, your value of y is getting smaller. So your y values start a little bit higher up. But as you move to the right, your x values are approaching 3. So here your x values at 0. Here your x values at 1, 2, 2.5, 2.75, 2.9, 2.9999999. And eventually, we're going to approach 3. We're going to get as close as we can, but we're not actually going to get there. Now, the tricky part about this is that students want to say, well, isn't the limit at 3, 7? No. And you're going to notice this by just looking at your left and right hand limits. As I approach 3 from the left, the y value that I'm approaching is 4. I'm not actually approaching 7. I'm approaching 4. And that's all that matters. We're just talking about what y value we approach. And you'll see the same behavior on the right for the same reason. As our x values approach 3 from the right, I'm just getting closer and closer and closer, following my function path. And here I am at maybe like x equals 4, x equals 3.5, x equals 3.25, x equals 3.1, 3.01, 3.001, so on and so forth. I'm approaching a y value of 4. I'm not going to actually obtain it, but it's the value that I'm getting closer and closer and closer to. And then sometimes students are like, okay, well, I can see the one-sided limits, but then why isn't the limit as x approaches 3 equal to 7? It's because the limit is not the same thing as the function value. F of 3 is 7, but the limit as x approaches 3 of f of x is 4. It's going to be equal to the same value as the left and right-hand limits, assuming those two agree. If the left and the right-hand limits are the same, then that's the limit that your function value is going to take on as you approach 3. Note, f of 3 equals 7, which is not equal to your limit value. Okay, so your function value at 3 is 7. The limit value is the value you're approaching. The function value is the value you're actually sitting on. So that's one example that tends to catch students. Who's raising their hand? Oh, Burfin. What's your question?
So, would it be possible to get like a different number though? Because like, you know how you said it's symmetrical on both sides. So even though it's like negative or positive, it's going to be the same.
Yeah, we're gonna do that next. Actually, you're like
Oh, okay.
reading my mind.
Okay.
Yeah, we're gonna do that next. Yes. Anyone else questions on B? I mean, I want to give you several examples so you have seen a lot of things and you have an idea of what to expect. Okay, so this time I'm going to put a point at 3, 3, and we're going to fill it in. Close circle at 3, 3. And I'm going to send your graph off, yoink, kind of up like that. And then I want to put a point at 3, 1, and I'm going to leave it as an open circle. And we're going to send your graph off to the left like that. Okay. Now remember, we're looking at the limit as x approaches 3 from the left. Don't forget your f of x. The limit as x approaches 3 from the right. And your limit as x approaches 3. I have sometimes asked questions like this on tests where I'll give you a graph that might look something like this, and I ask you to find these limits. And this is where students will always forget their f of x's. I'm not actually giving you a function definition here, so you can just leave it as f of x. Okay. As x approaches 3 from the left, you're moving along the left leg of this curve here. As x approaches 3, the value that y approaches is 1. So I would say that the limit as x approaches 3 from the left is 1. Questions about that? Another reason it's kind of good for you to turn on your cameras is because I say, if I say, does anyone have a question about that? And I see a bunch of people doing this, then I'll have a good idea that like, okay, you're with me. But if I can't see anybody, I'm just like, oh, like, I hope they're fine. As x approaches 3 from the right, I'm following this right leg of my graph. I'm just heading downward. And the y values get smaller and smaller and smaller, and they eventually approach 3. If your left and right hand limits do not agree, then the limit of the function cannot possibly exist at that particular value of c. So in this case, the limit as x approaches 3, if I'm just talking about the general limit, not the one-sided limit, does not exist. And sometimes students think, well, technically, wouldn't it be 3 because the function value actually exists there? No, because in order for the limit to exist, your function value must be approaching the same value from both sides. You have to have some situation where on each side of your function, you're approaching a particular value of y. That's not happening here. If the left and right hand limits do not agree, then it can't be possible that the limit actually exists at that point. So you can say the left and right limits do not agree. And if you want to just say DNE for does not exist, that's what I'm going to do in the future. I just write DNE. So that was sort of what I wanted to say about graphically. The other piece of that would be the piecewise functions, which I wanted to do next. Before I do that, did anyone have a question that wasn't cleared up by going through examples A, B, and C? These are just different scenarios. In A, you had that the limits agreed on both sides. The function value wasn't actually defined there. In B, we defined the function, but we had it defined elsewhere. And then in C, we had a situation where the left and right limits did not agree. Let's do some piecewise functions because we always need work with piecewise functions. Always. Always. Example 3. Use the graph to investigate the limit. And this is my last example for 1-1. Well, it's actually like a 3-parter. F of x equals, and I'm going to make this a piecewise function that has 2 definitions. One of them is 2x plus 1, and that's if x is less than or equal to 0. And 2x if x is greater than 0. And we're going to investigate this at c equals 0. That's really the only interesting place at which to investigate this limit because 0 is your boundary. Now, if you want to graph these functions using y equals mx plus b, that is fine. Do that. If you want to graph them just by using a table of values, that's also fine. It is up to you. I'm not testing you on your ability to use y equals mx plus b, so there is no shame in the game if you decide that you want to use a table of values. You can absolutely do that. Sometimes I do that just because I know everybody knows what I'm doing and I don't have to worry about refreshing them on y equals mx plus b. Okay. If x is greater than 0, if you're going to do this using a table of values, and you don't have to even write it out specifically, but I'm going to do it just because I think that it might be helpful. I want to talk about what actually happens at 0, because there are actually 2 different, even though 0 is technically only included in the first definition, we do want to approach a value here, so we want to make sure that we include that open circle. So let's talk about f of x, and then we'll get an open value for one of them. Okay, so at 0, technically we're looking at our first definition, but let's talk about the second one first, because I think sometimes it's easier just to graph the right-hand side of this function. Now, 2x, if you feel like, okay, yeah, I got it. The slope is 2, the y-intercept is 0, fine, just graph it. But if we're looking at f of x equals 2x, then we have a y value at 0. And in this case, it's going to have to be an open circle. So we'll leave the open circle at 0, 0. And then you can look at values like 1, 2, and 3. And if f of x equals 2x, well, 2 times 1 is 2. 2 times 2 is 4, and 2 times 3 is 6. Now, it's up to you how you want to label this. We don't need to get too crazy with how far we go, but we know we at least need to go up to 6. So I might leave a little bit of extra space because I don't know what's going to happen on the other side. So I have a point at 1, 2. I have a point at 2, 4. And then I have a point at 3, 6. And then at that point, we pretty much can figure out what's happening from there on out. And we'll go ahead and connect these with a nice line, and we'll pop an arrow onto it so that we can indicate that that behavior continues throughout the domain of the function. Just don't forget to include the point at this boundary with an open circle. Otherwise, you're going to have some issues with continuity next week. So be careful there. So I do want you to evaluate the function at the boundary, even if it's not included. Just don't forget your open circle. The other function occurs at values of x that are less than 0 or less than or equal to 0, I should say. So maybe if you want to just make one more table and put it over here. Yikes. I ran into my document camera that I love so much. F of x is 2x plus 1. And if you're just like, yeah, I get it, 2x plus 1 is just shifted up 1 unit, no big deal. That's fine, do that too. 0, -1, -2, -3. 2 times 0 is 0 plus 1 is 1. 2 times -1 plus 1 is -2 plus 1, which is -1. And these values are linear, so you should see that these are changing by the same amount each time. So 2 times -2 plus 1 is -4 plus 1, which is -3. So you can see that these are going to decrease by 2 each time, which makes sense because of the slope. -5. Okay, so we'll go ahead and put a point at 0, 1, and this one should be a filled-in circle. And then at -1, -1. And then you can see how now this behavior is going to continue as you move down and to the left. Sorry, my scale is going to be off. This would actually be easier if I just kind of did it visually. These should be parallel lines. But, you know, we're kind of subject to how well we can draw. Mine is just getting worse as I continue to try to fix it. But there's your piecewise function. And now we have to investigate the limits. So I know sometimes we get so carried away with just drawing these piecewise functions that we forget that we had to do something else, which was investigate the limits. Before I do that, does anyone have a question about the graphing of the piecewise function? Wonderful. So let's look at the limit as x approaches 0 from the left. And you can just write f of x. You don't have to write the whole function out. The limit as x approaches 0 from the right. And then we'll talk about the limit as x approaches 0. Okay, so now clearly you can see that there's an issue here. But let's go ahead and look and actually get some values here for these left and right limits. As x approaches 0 from the left, I'm sitting here on this left leg of my function here on this line 2x plus 1. As x approaches 0 from the left, the y values are going up, 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 up. And then as x approaches 0, y is approaching this point at 1. So we had that 0, 1. We could say that the limit is 1, regardless of the fact that we were able to obtain that point. Okay. I always find it so ridiculous when my watch tells me I'm achieving all of my fitness goals while I sit here. I guess, I mean, I'm talking and like waving my arms around. Anyway, ridiculous. Okay. So the limit as x approaches 0 from the left is 1. Do the same thing as you approach 0 from the right. So from the right, I'm sitting at this line, 2x. As I approach from the right, even though I'm not actually attaining the point 0, 0, I'm getting there. So the value of y that I'm approaching is actually 0. But your left and your right limits do not agree. And I think visually you should be able to start to see this. If you've got this big gap where you're not approaching the same value on both sides, kind of like C in that last example that we did, then the limit's not going to exist. You can verify that just by finding the left and the right side limits. If they don't agree, well, then your limit at that point 0 is not going to exist. You see this big disconnect, that's a problem. And we'll talk about that later in terms of continuity. Today we're talking about it in terms of one-sided limits and whether or not our limit exists at that point. But let's do another one where you see something kind of similar, but we'll make it a little bit different. Before I do that, does anyone have a question on A? All right, so B. Oh, I got to give you a function definition, don't I? Not giving you that. What am I doing? Okay, f of x, and I'm going to give you a function that is defined in 3 parts. X plus 2 if x is less than 2, or if x equals 2, and x squared if x is greater than 2. Now, if you want, you can go ahead and plot the point at 2, 4, because that one is going to be the easiest one to do. But clearly your boundary is occurring here at 2. So that's where we're going to look at this limit at c equals 2. At c equals 2. All right, now you can draw your coordinate axes. By the way, in like 7 weeks, when you guys are preparing to take your final exam, you're going to be looking back at this and being like, I don't even remember doing this, because there's going to be so much that happens between now and then that you're going to be like, wait, what's a limit again? I don't even remember doing those. It happens every time I teach Calc 1. The students are like, oh my gosh, I have to like remind myself of what limits are. So even though it seems like it's your whole world now, it'll be a distant memory. All right, so I know something's happening at 2. I've got a point at 2, 4. I'm going to go ahead and put that on here. I know that for x being less than 2, I'm looking at x plus 2. Now, if you want to use y equals mx plus b, I think that's going to be faster here than making a table of values. So as I approach 2 from the left, I'm looking at x plus 2. So 2 is your y-intercept. That's right here. And then the slope is 1. So you're going to go up 1 over 1, up 1 over 1. Now, technically, on this function, you would have an open circle, but when you went to open it, it was already closed. So if you want to see that again, forget that I graphed this. I probably should have waited. I just got ahead of myself. I got so excited that we had something easy to graph. But let's imagine we didn't put that on here. You looked at, okay, what happens at 2? Well, 2 plus 2 is 4. You would have this open circle. But then the second definition of your function says that when x equals 2, the function value is 4. Then you would say, wow, I no longer have an open circle. Close the circle. So that's why the circle's closed. It's not because of the first piece of this definition, it's the second piece. So technically, if you did not have this line, if the second line of your function definition was taken out, then we still would have had an open circle here. Okay. So we've already done the first 2 lines questions so far. Okay, and I was saying this in the office hour, but also just make sure your function's doing what it's supposed to be doing, especially if you don't use a table of values. The slope is positive, so you know it should be going up from left to right. So just verify that that's happening. You'd be surprised how often that gets messed up. And then x squared if x is greater than 2. If you find it easier to use a table of values for that one, that's fine. Just remember that if you do that, start it at the boundary point. Even though you're going to have an open circle there, doesn't matter. Just make sure you evaluate it there and leave the circle open. So maybe we would do 2, 3, 4 is really not going to matter for us because we're not going to be able to graph that point. 2 squared is 4, 3 squared is 9, 4 squared is 16. But this is a parabola. Technically, if you feel comfortable graphing parabolas, but maybe you didn't know how to do it piecewise, you could always graph the whole thing and then erase what you don't need. But you have a point here at 2, 4. Well, guess what? It's already filled in. You were going to leave it as an open circle. And technically, it should be open for the last definition of this function, but it's closed because of this middle line. At 3, 9, you have another point. And you can kind of now see the behavior of this parabola. It would have gone up like that. That doesn't exist over there. Kind of does something like that now. Okay. Questions on the graph before we look at the limits? So we'll look at the left limit as x approaches 2 from the left. We'll look at x approaching 2 from the right. And just the limit then as x approaches 2. So as x approaches 2 from the left, you can see that your y value approaches 4. It's filled in here. It doesn't matter. All that matters is that you're approaching 4. As we approach 2 from the right, you're following this parabola. And again, you have this point at 2, 4. So as you approach 2 from the right, you're still going to be approaching this y value at 4. Now, the left and the right limits agree. Whether the circle's filled in or not does not matter. You can say that the limit is the same on both sides as we approach x equals 2. And we can make a conclusion that the limit is 4. Now, I wonder if some of you were thinking, well, what if we had this, but we didn't have this? Like, what if that wasn't there? If that was the case, the only thing that would change would be that this circle would be empty. It wouldn't be filled in, but it wouldn't affect the limits at all. So if this condition is taken out, the limits don't change. It would just be the case that the circle would still be open at 2, 4. The circle would be open at 2, 4. That is the only thing that would change. It wouldn't actually affect the limits. It would just change the fact that your circle is empty instead of filled in. That's it. Any questions on that example? Are you guys feeling more comfortable with piecewise functions at this point? Yikes. How do we feel? This would be a good time to have your cameras on, and then you could be like this, or you could be like, Yeah, we get the so-so. The so-so is helpful too, because I can think like, maybe they would like to see one more example. I guess I'm just thinking like, I have 9 minutes left, and I really don't have enough time to get into 1-2 at all. I don't want to really introduce something in 1-2 because there's nothing that I can introduce very quickly in there. It's better if I have it all together. But I mean, we're not in a huge hurry because I still have tomorrow to do 1-2, 1-2 and start 1-3. And then I'll make your asynchronous 1-3 and part of 1-4. So we're actually good to go. You guys want to see one more example of a piecewise function? I have one prepared for you.
Yes, please.
Yes. All right. I feel like students don't usually say no to that. More examples on piecewise functions are better. Okay. Oh, by the way, you might have noticed this. If you don't get notifications in D2L, you should set them up. It's somewhere in your settings, notifications. I re-uploaded the syllabus because somebody pointed out to me that the dates I had for tests 1 and 2 were on like Sundays. And I don't know how that happened. I think I know how it happened because I normally don't set your tentative schedule to start on a Sunday. If we start class on a Monday, I usually have it start on a Monday. And I didn't look at an actual calendar. I just looked at your tentative schedule. So I think I took the first date of the week and assumed it was a Monday, but it was actually a Sunday. I fixed it. I uploaded it. So your first exam is not supposed to be I don't even want to say what it is because I have the old copy of it in here. It's not the 20th, which is a Sunday, or whatever weird thing I set it to. So yeah. Look at it again, but I re-uploaded it to D2L just so you know that the first, now I feel like I mentioned it and I kind of have to say something. Oh, you know what though? I emailed it to the secretary today, so it should be right there. Maybe someone has it at their disposal and they can tell me even faster. Let's see. All right, it says here, your first test is supposed to actually be the 17th, which might be sad for some of you because it's actually earlier than you had anticipated, but I believe that's next week, Thursday. Yeah, next week, Thursday. So yeah, we'll see exactly what's going to be on there. You will definitely know in advance, but yeah, 17th. I don't like having tests on Thursdays, but in the summer, I sometimes don't have a choice. But let's kind of see. If we can move it to a Wednesday, you might like that better because you have Tuesday off. But if there's something I'm covering on Wednesday, it's not as likely I would put that on a Thursday test. But then I don't like to cover stuff and not test you over it because then you don't care about what I'm covering because it's not on your test. See the conundrum that occurs here. F of x. I'm going to give you a 2 definition function here. Your pieces are x cubed and x squared minus 1. So x cubed if x is less than -1, x squared minus 1 if x is greater than -1. And of course, we're going to evaluate this limit at -1, the only interesting place to do so. If you want to use a table of values, fine. I have a feeling that that's what you guys will be doing. So that's what I'm going to do. I'm going to start out with the second definition just because it's the one that's on the right. For some reason, that always seems like people like it better. I'm going to start it at -1, even though it's not defined at -1, and I'm going to leave it open. I'm going to even make a note to myself to leave it open so I don't forget to. -1 squared is +1, -1 is 0. And then at 0, 0 squared is 0, minus 1 is -1. You can even pop these into your calculator table if you want to get them a little bit faster. That's up to you. I mean, a table is a table, right? 1 squared is 1, minus 1 is 0, 2 squared is 4, minus 1 is 3, 3 squared is 9, minus 1 is 8. If you feel really comfortable using your library of functions in your translations, you might just want to graph a standard parabola and shift it down 1 unit. That also works. But here's what you have. You're shifting your standard parabola down 1 unit. You have the open circle at -1, 0. And then you just are going to carry through the behavior of your parabola. And at this point, it doesn't even matter. All you care about is what's happening at this boundary point. So don't feel like, oh my gosh, I have to graph this whole thing and it has to be perfect. It should look like a parabola. It should have an open circle at -1, 0. Other than that, doesn't matter. For your cubic function, again, we're going to start this off at -1. Even though it's not defined there, we're going to make a note to leave it open. And then we'll go left. So -2, -3, -4. And this is a cubic function. So obviously we can't go very far with it because these numbers are going to get really big really fast. -1 cubed is -1 times -1 times -1. Stays negative. -2 cubed is -8. -3 cubed is -27. Remember, if you're squaring values in your calculator, to put parentheses around them if they're negative. This is a very, very common algebra mistake. -2 squared is not the same as -2 squared. One of them's -4, the other one is +4. This one takes 2, squares it, and puts a negative in front of it. The second one takes -2 and multiplies it by itself. Big difference. Make sure if you're squaring a negative, you remember that. All right, so I have an open circle at -1, -1, which is right about there. And then I have a point at -2, -8, which is approximately right here. And then whatever else happens, I know it's going to look linear. It's not linear, but actually it's going to slightly curve downward, but it does not matter. You get the gist. So let's go ahead and talk about the limits. Does anyone have a question on the piecewise function? So remember, we're looking at x approaching -1. We'll do that from the left, from the right, and then we'll just take that general limit as x approaches -1. Now, remember that in the last example I went over, we had another situation where we had this piecewise function. It had a lot of different pieces, but in that case, they all were connected. And because they were connected, that really meant something in terms of our limit. Even though this wasn't filled in, that didn't even matter because they were approaching the same value as we approach from the left and the right. That's not actually happening with this function. As I approach -1 from the left, I'm sitting on this curve on the left. I know it doesn't look curvy, but it is. As I approach -1 from the left, my y value also approaches -1. So the limit is -1 as I approach -1 from the left. But as I approach -1 from the right, now I'm sitting on my parabola. I'm going to approach from the right, and my x values are going to get smaller and smaller and smaller until I eventually approach a y value of 0. So if I'm sitting on the x-axis, my y value is 0. The left and the right limits do not agree. Therefore, the limit of the function does not exist. And it is exactly 810. I can't believe I got that just right tonight. That's it for 1-1. I'm done with 1-1. I'm going to put up a homework assignment for 1-1 for you. It is going to be due Friday at 6 p.m. I know we don't have class on Friday, but you have 48 hours to do this homework that I'm going to put up for 1-1. I tend to think this 1-1 homework is not quite as tricky. Just because it's a little bit more concentrated than the review homework that you had. But I'm gonna have to run in a minute, but I'm gonna put this up, and the Google Drive video link for the class should be up in the calendar. But I'm also gonna upload it to YouTube. The class from 2 days ago is on YouTube. Also, there's a YouTube link on D2L. If you're new to the class and you just registered, your D2L might not be available until tomorrow. So, but if you, I'll have to invite you to the class in the calendar. Oh shoot, someone registered and I never sent them a link. Yowza. Okay, I have to do that now. Anyway, that is all I have for tonight. I'm gonna see you tomorrow night at 6 p.m. Have a wonderful evening.
I have a quick question.
Sure.
Do we have a quiz tomorrow?
Oh yes, quiz tomorrow. I'm so glad you reminded me. Yeah, the syllabus does state Mondays and Thursdays. So yeah, you will have a quiz tomorrow. I'm not gonna make it over the review material though. It's just gonna cover 1-1. That's it. It'll be pretty quick, obviously.
Okay, thank you.
You're welcome. Stop recording.